Okay, welcome to the next class on variational methods for computer vision. Last time we talked about the Mumford-Shah functional, and I'm starting with that slide again. Here you see the Mumford-Shah functional. As I mentioned, it has three terms. One is the quadratic data term, one is a quadratic smoothness term, but the key smart thing about it is that the smoothness term is adaptive in the sense that smoothness is not penalized for all pixels, but only for those pixels where you don't have a discontinuity set C or boundary, if you will. And so the idea is that you do a smooth approximation, but it's actually only piecewise smooth in the sense that you have a discontinuity set C where you allow the approximation U to jump, to be discontinuous. And so there are two weighting parameters, lambda and nu, that weight the smoothness and the penalty for the discontinuities. And you can imagine what these two parameters will do. If you crank up lambda, then you impose more and more smoothness. If you crank up nu, then you penalize discontinuities more and more. One thing I mentioned last time, and there was a question about it, a very good question, and that was, later we saw that there is an approximation which arises for lambda going to infinity. And I mentioned the idea is that you have a signal which is a bit noisy, has discontinuities, is noisy, but the underlying true signal should be smooth, and then or piecewise smooth, and then the approximation of the Mumford-Shah would be something that has jumps, but in between the jumps is smooth. And then if you crank up that smoothness, so for large lambda, if we let lambda go to large values, let's say large, then the smoothness is enforced more and more, such that ultimately the approximation becomes constant. And then we end up with a cost function of this type. And then someone was arguing that indeed, don't you get exactly this cost function if you set lambda equals 0? Right? So if we go into this energy and set lambda equals 0, then indeed we get this cost function. That is true. And in fact, you can read it like that in books. The book of Korn, Probst and Aubert, for example, which is by and large a good book, it actually says that if you drop that term, you get the piecewise constant approximation. And in fact, it still says it in the second edition, although I told them this is not quite correct. The issue is you get this expression if you let lambda go to, if you set lambda equals 0. But what we want is not just this cost function with the function u here, but we want the constraint that you see below, that u is constant in each of the separated regions. So we want to say minimize u, minimize this integral f minus u squared dx plus nu times c, such under the constraint that u is constant in all regions. And this is the important constraint, and that only comes for lambda going to infinity. For lambda going to 0, you of course get the same cost function, min u minus f squared dx plus nu times boundary length, but that cost function is a bit strange, u and c, one should say, because in this cost function, if you don't have that constraint, then c and u have nothing to do with each other, right? So you can, for example, just choose u equals f, that solves your problem, right? That minimizes this cost function because u is not constrained to be constant. U can be anything, and so, set u equals f, you have the minimum. And so there is a fundamental difference in the limit of lambda going to infinity and lambda going to 0. Lambda going to 0 means you drop that term, but that makes the whole approach somewhat meaningless. And so it is really the piecewise constant approximation only emerges in the limit lambda going to infinity. because you penalize smoothness more and more, and with larger lambdas the thing gets smoother and smoother until at some point it is in the limit of stronger smoothness, it is constant. And then you can rewrite it in this way. Once you know U is constant in each region, you can also rewrite it by writing wherever U appears, you write these constants. You call them Ui, is the constants in the various regions. The formulation, there are different, as I say, different notations for this approach. Rather than writing C here and the boundary lengths of C, you could also write omega 1 through omega n, the various regions. So you're optimizing. Optimizing for the boundary essentially means that you optimize for the regions omega I. And the coupling between these two terms arises because C is the boundary that separates these regions. And determining the regions implies that you determine the boundary. I already discussed the discrete analog, the Ising model. Here is a minimization of the Ising model, which shows that indeed this boundary length is a very powerful regularizer. And it is become extremely popular, in particular once we started having algorithms that can actually minimize this globally, at least in the two-region case. And so, to some extent, one could argue today that the two-region segmentation case, at least from an algorithmic point of view, is solved, at least for this class of cost functions, let's say. That is actually, again, not quite right. Nothing is ever fully solved in our field of research. This is solved once you fix these values Ui. So once you know what the, say, mean intensity in each region is, in fact these are these constants here, then the binary segmentation is solvable in polynomial time.
Plus you have to know which constant is.
That is not necessary. This question of which pixel corresponds to which region is actually solved by the optimization over the regions and by this binary labeling of regions. So in the optimization, here you see it, each pixel is assigned a value 0, 1 or plus 1, minus 1. There's different notations of this cost function. And this labeling, the optimization in the variable U, is polynomial in the number of pixels. In practice, for image segmentation, it's often even linear in the runtimes, which means it's really fast. In practice means the fastest existing algorithms to solve this problem. One of the fastest is the Boykov-Kolmogorov algorithm, and that is not strictly speaking polynomial. It's only pseudo-polynomial, but the runtime in practice tends to be linear. But this is a whole, as I said, separate issue. We'll not be talking about graph cuts here. There's a zoo of algorithms, new algorithms coming out every few years on how to make this more efficient and faster. Because it's an important practical application that can profit from getting faster solutions. Today we'll continue with the Mumford-Shah model, and we'll talk about some insights into the Mumford-Shah functional, some mathematical results that were obtained, then regarding minimization, the Euler-Lagrange equation, and we'll find that this is not as straightforward as the standard Euler-Lagrange calculus, and I'll show you in a second why. And then we'll come to statistical interpretations that allow a generalization to other domains. Some mathematical insights. If we look at the cost function, as I said, it contains two variables. These values Ui, here we have them, these brightness constants for each region omega I, and then the boundary C. And in practice, a lot of the algorithms, in fact, what is currently mostly done to minimize such energies, mostly means there are other results as well. But what's mostly done is that you alternate the optimization in the boundary and the average gray values. And that is very much in the same spirit as the clustering I mentioned earlier. When you group the pixels based on their intensity or color into groups, you tend to alternate, associating a group, say a Gaussian distribution for each, and then assigning each pixel based on its color to the closest Gaussian. And so similarly here, the model parameters representing each region are optimized in alternation with the region assignment. And as I said, once you fix the parameters, in a two-region case, you can actually solve the assignment for the given model optimally. And we'll see in a second that finding the region parameters is actually trivial to solve in closed form. Let's look at that part first because it's easy. How do you minimize this energy with respect to UI? Well, here you don't have to have any sophisticated Euler-Lagrange calculus because UI are just scalar values. It's just a number. And so how do we do it? We take the derivative with respect to UI and set it to 0. The standard way to determine minimizers. This is obviously quadratic in UI, so it's convex, and which means that there is only one minimum. And in fact, if you take the derivative, you get a linear equation system. The square comes down, you get 2 times this expression equals 0, and then you just solve for UI. So what you have here is the integral omega of I of the input brightness dx minus the integral omega I times ui dx. But ui is a constant, so we can actually pull this out of the integral, divide by the integral, and what we're left with is this. And what this is, it looks maybe a bit strange at the first glance, but it really just is the average brightness of the region. And that's not surprising, because what are we doing here? We're saying find a constant ui such that it fits the observed intensities in a least squares manner. And if you do least squares optimization in this context, you know what you get is the mean intensity, the average intensity. And so we just re-derived that, what's already somewhat standard knowledge. This is the sum intensity divided by the number of pixels, essentially. And so it just gives you the average brightness in region omega I. And so in fact, the segmentation, the way this is done, is typically done by alternation, that you start with some initial configuration, you assign to each of the initial regions their average brightness. That's very fast to compute. And then you update the boundary. You update the regions. And this actually turns out to be the key challenge. The key challenge is finding the segmentation, and ultimately the difficulty is that all of these energies are not convex with respect to the boundary. But let's first look at what results we have. So one thing we can do is we can solve this for u in closed form. We can actually take that ui, this expression here, and insert it back into this energy. And what we end up with is a cost function that only depends on the boundary. It no longer depends on ui's because we can solve for ui in closed form and insert that in here. The reason why in practice you do alternation and you don't insert it in here is because the dependency on omega I is already pretty bad. And if you take this expression that has a numerator and a denominator that those both depend on omega I and insert that in here, you have such a complicated dependency on omega I that it makes the whole optimization problem more nasty. And so typically one doesn't plug it in here but rather alternates. But in principle you can plug it in here, and then with a slight abuse of notation you get an energy that only depends on the boundary. Some results on this energy, E of C, let's call it. The minimizing boundary, C, they are closed, and differentiable up to discontinuities of the following type. So these are results that were proven in a number of papers in the literature, starting with the original Mumford-Shah paper.
This alternative iterative approach, does one have to know that how many regions there are?
Good question. So the question is, do we have to know how many regions? Because we have a little n here, and the question is, what is n? In this approach, yes. Once you alternate, you have to start very much like in k-means clustering. This is our k. We call it n here, but it's the same, really. And in k-means clustering as well, you have to determine k. That said, there are algorithms that automatically determine it along with everything else. Because indeed, this was a bit glossing over details. When we took the limit lambda going into infinity, we saw that we get a piecewise constant approximation. But this is indeed a bit simplifying things, because in the piecewise constant case, we have a variable n here, that a new parameter that wasn't there before. In principle, we do not need that parameter. In principle, this length regularity actually tells you what the right number of regions is. Because if you increase the regularity of the boundary lengths, then the algorithm will typically find fewer regions. And we'll see a little later that dependency a little more explicitly. So in this alternation, you fix n, but there are ways to get it automatically. Essentially, you optimize over n as well. And in this case, you could run the same approach with different numbers of n and see which gives the lowest energy. And there's, of course, again, more elegant solutions to do that, which basically compute everything in one. So as I said, these results were proven in many papers, starting with the original Mumford-Shah paper. For example, one result or two results you find in the original Mumford-Shah paper is that the boundary is continuous and closed and differentiable, except for these two exceptional cases. And one is that three boundary segments meet at equal angles. So if you have a segmentation in the image with three boundaries meeting, then they meet at 120 degree angles. So it's all 120 degree angles. And in fact, you will never have four regions meeting in one point. That never happens. So rather than having four regions meet in one point, as so, what you're going to find is a result where you always have only three regions meeting. And then you have two so-called triple junctions. And the other result is that the boundary, once it hits the image, the end of the image domain, say here, then it meets it at 90 degree angle as well. So this is interesting without actually looking at the observation of the image, without actually looking at I for any given I. Once you minimize this cost function, you will only find these types of boundaries. Now you might wonder, why is that so? It's actually rather intuitive. Assume you had a boundary that met the end of the image at an angle alpha that was not 90 degrees. Assume that was your minimizer, then if you just infinitesimally change the curve so as to bend and get a 90 degree angle here, what you are doing in the process is you're reducing the boundary lengths. You can imagine that, right? If you have a boundary meeting like so, and if you bend it a little bit, the the lengths get shorter. And so you save in terms of length energy. In terms of the data fit, this infinitesimal change is negligible because it's basically, you can make it so small that it only affects 1 or 2 pixels or less actually in an infinitesimal setting. And so in terms of boundary cost, it's almost the same, but the length is being reduced. And so for any non-zero weight nu, you will see that the boundary will actually favor 90 degrees. So you can show that the original configuration, which had a smaller angle than 90 degrees, is not an optimum. that there is a slight perturbation that has 90-degree angle and it has lower energy because it has less boundary lengths. Similarly, you can argue that if three boundary segments meet in a point and they don't have 90 degrees, but maybe this one only has, say, 40 degrees or something like that, then by slightly bending that triple junction and moving it here, you reduce the boundary lengths again without essentially affecting that term. And so ultimately the reason for these results on the boundary configurations are due to the fact that this term measures a regional property and this term measures a property of the boundary lengths. And so infinitesimal changes are negligible with respect to the data term, but they do affect the boundary. And so that is ultimately the reason. The proofs, you can imagine, are a little longer and technical, but this is the intuition behind these results. In general, the minima of this energy are not unique. So typically you will have multiple minima, and there are lots of examples where you have multiple optima of the same cost, actually. So even the global minimum is not always unique. To give you one example why the global minimum is not unique, clearly in the cost function you have a competition between a data fidelity term and a boundary length term. And you can imagine a case of this type where you have a circle where the circle, say, is black, the area inside the circle is black, the background is white. Maybe I should put that on the other board. You have as an input image, so the brightness intensity I is black inside, white outside. So the result, or one result that you would expect from a segmentation of the Mumford-Shah would be a boundary that is here, right? And indeed that will typically be the result, except if you crank up the weight nu, right? If you crank up the boundary length penalty, at some point, if this circle, say, is radius r, then the boundary length is 2 pi r, and that is the cost you're paying here. And what you gain is you have a better fit because you can set the constant outside to white and inside to black, and so the data term is 0 and all you pay is 2 pi r. But at some point, if nu, 2 pi r times nu, of course, the weight of this length regularity. And now you can imagine if you crank up the nu, at some point, if nu is sufficiently large, the better solution is actually the empty set, no boundary at all. Because then you have no length regularity, you don't pay for length, and all you pay is a term that depends on how bad the fit is, because then you would have just one constant to represent the whole image, one brightness constant, because you only have one region then. And so you would have to choose a constant that is somewhere the average gray value of the image. And then you pay a little bit on the data term, but you don't pay on the lengths. And you can imagine there is a value of nu where the trade-off is the same. So for a specific value of nu, both solutions have the same cost. And so then you are in a case where you can either have a result where the disk is segmented or a result where the disk is not segmented and where it's just one region. And for that value of nu, both solutions are the same. And now if you generalize that to 2 of such disks, you can do the same case, and then you can imagine you can get a parameter value of nu where you have many possible solutions. One the empty set, one just one disk, one just the other disk, one both disks, etc. And so all of a sudden you have cases of multiple solutions that have the same cost. Because the cost is always based on a competition between a data fit and a regularity term. And if the regularity term is strong enough, then there is ambiguous solutions. Now we come to the Euler-Lagrange equations, and this is a little bit tricky because the functional, as we saw it, is not in what we call the canonical form. You remember the canonical form we called energies of the type where your argument, say, let's say it's u, is an integral of a Lagrange density that depends on u, and say the derivative of u dx, if x is your running variable. And here we don't have this form. Here we are so the cost function depends on c, and as you can see, as you can check, where is c in your cost function? It's in the integration domains. There's hardly any more nasty point to put the variable than in the integration domain, right? Because if we go back, we're optimizing for c now. The u's we assume are known. But c actually affects the regions omega I, and we're integrating over the regions, and so the cost is not just in the integral, but really in the integration domain. More specifically, let's assume we just have a simple boundary, c, and then we have a cost where, let's say, we have two regions. We have an inside of the boundary and an outside of the boundary. So for now, let's assume we have a curve C in the image, and this we call the interior of C. That is the one region, and then this we call the exterior of C, the other region. Right? So these are the two regions that are separated by this boundary. And so the cost function that we have is some integrand that is integrated over the interior of the boundary. And now we want to compute Euler-Lagrange equations with respect to that boundary C. There are many ways to do that, and I decided for one particular approach that was promoted by Sungchun Ju, a professor at UCLA, and he was using Green's theorem to derive it. So we assume we have a parametric boundary, a boundary, as I mentioned last time, that maps an interval 0, 1 to the image domain. And typically we assume it's a closed curve, so C of 0 equals C of 1. This is the cost function. We will generally just write f, some integrand. For now, it doesn't matter what it is. So this integrand, for example, in the Mumford-Shah would be that expression here, I minus u squared, but it could be some other expression. That's not really important, so we just call it f. Now comes the key idea. As you see, the cost function is of this form, and the optimization variable is in the integration domain. But we want to map it back to this canonical form. And so we do that in two steps. First, we rewrite the integration over the interior of the boundary as an integration along the boundary, C. And then we parameterize that boundary from 0 to 1, as you see here, and then we end up with this, what I call canonical form. Because the domain that C is defined over is the interval 0, 1, and so this is really the canonical form. How does it work? Well, turns out you can rewrite integration over a region as an integration over the boundary. This is called Green's theorem, sometimes also called Stokes' theorem. Essentially, for those who haven't heard of this before, it arises in multivariate analysis and is the generalization of the integration by parts. And as you know, integration by parts means that you can do an integral over an interval and replace it by a cost that is evaluated on the boundary. And here we do the same. So you can, if you have generally a vector field V, there are many forms of this Green's theorem, but that is the most commonly seen form. It says that if you have a vector field defined on R2, then the rotation of this vector field integrated over its interior is the same as the vector field itself integrated along the boundary. It's actually quite interesting that you have such relations, because it means that rather than evaluating something, some expression in the entire interior, it suffices to evaluate something along the boundary. And this holds for any vector field. And so what we'll do now is we'll basically define a vector field so that we can rewrite our integral, where was it? Here, f over the interior as some integral across the boundary, along the boundary. Yes?
This doesn't require this constancy, right? Or does it?
Which constancy?
We now use the constancy.
Oh, you're right, it doesn't. This also holds for the piecewise smooth approximation, but in some sense it assumes that you have a closed boundary. And this is an issue, as I mentioned, the original piecewise smooth approximation also allows open boundaries. So this calculus doesn't apply to the open boundary case, because the Green's theorem assumes that you have a closed boundary. But apart from that technicality, the same extends also. Then f, you're quite right, f would not be just u minus I squared, but it would be u minus I squared plus nabla u squared. So whatever it is, you can, and we'll see an example where we apply exactly this approach to the piecewise smooth approximation. So what do? We just assume that there is a vector field V such that the rotation of V is f. So more specifically, the rotation of V, by the way, if V has components A and B, the vector field, then rotation V is dx of B minus dy of A. That's how it's defined. And so this Green's theorem, if we write it with A and B, it says that the rotation of V, so Bx, that is the x derivative of B this here, minus Ay, the y derivative of A, integrated over the interior is the same as integral of V ds, so that would be A dx plus B dy. Because ds essentially is dx and dy. And now we say choose a vector field V such that f is bx minus ay. In fact, I don't show this here, but there exist vector fields for any f. You can find a vector field that this holds. So f is the rotation of V. And then we can rewrite the integral f, that's our original cost function that we started with, as integral of this expression over the interior, and then integral of c of a dx b dy. And now we rewrite that again by writing a of dx by ds times ds and dy by ds times ds. So we just replace the dy as dy by ds times ds. Why do we do that? Because then we can write it as an integral not along the boundary, but over the parameter interval of our boundary. And so then we have it in this, what we call canonical form. Some cost that is aggregated over the parameter interval of our unknown variable, C. So to restate that, the integration of f over the interior can be written as an integration over the parameter interval of the boundary. And once we have that, we can now apply the standard Euler-Lagrange calculus. Because now it's in the canonical form, so then we can say dE by dC, and C has two components, x and y, right? C of S is x of S and y of S. And so there are actually two Euler-Lagrange equations, one for the first component and one for the second component of the curve. With respect to the first component, let's look at that. So we have to do dl by dx minus dds dl by dx prime. That is the Euler-Lagrange functional gradient with respect to x of s. How do we do that? Well, let's look at this. At a first glance, it seems there is no x dependency, but really A depends on x, right? A was the component of the vector field, and it has an x dependency. So we have the d by dx is just dA by dx times x dot. And then we have b also depends on x, so we have db by dx times y dot. And then from the second term we get d by ds of dl by dx dot, and that is just a, right? And now we can expand this last term, because a depends on x and y depend on s. So when we have a here, what we really have is a of x of s and y of s. And so dA by ds can be written as dA by dx times x dot. And so if we have here minus dA by dx times x dot, that term cancels with this one. And then we have minus dA by dy times y dot, and that is the term that I put here. And so regrouping all the terms, we have y dot times dB by dx minus from here dA by dy. It's a little bit involved, the calculus. I recommend go through it at home and see if you can rederive it. This is typically a very helpful exercise to get a little bit familiar with these calculations. But what's interesting is what you end up with here, dB dx minus dA dy, is exactly f. So that function f reappears in a way that we can actually safely ignore what a and b really are. We can just plug in f again. And similarly, you can do the same calculation for y of s, and it's quite analogous. You expand that term here, and one of the two terms cancels, the other one remains, and what you end up with is minus f times x dot. So the whole lengthy calculation can be compressed in very short result, saying that dE by dC, the functional gradient of that energy with respect to C, is just f times y dot minus x dot. And it turns out that this vector here, y dot and minus x dot, where x and y represent the curve, is nothing but the outer normal on the curve. So for our curve here, where do I have the curve? Here. This is the outer normal, is a vector, a unit vector pointing outward. And that's exactly this vector here. X dot, y dot is the tangent vector. And then if you rotate that 90 degrees to have it point outwards, you just get y dot minus x dot. You can check for yourself, because the tangent vector is always x dot y dot, and of course the tangent and the normal must be orthogonal, and you can check x dot y dot times y dot minus x dot is indeed 0. So these are really orthogonal, and so that shows you that indeed this is the normal. Right, so we have the normal, and so the whole Euler-Lagrange functional gradient says the energy change with respect to the boundary C is nothing but f times the normal. It's a lengthy calculation, and it's a little bit surprising at a first glance that such a simple result comes out, but I want to a little bit show you that intuitively that result really makes sense. Because what do we have? The cost function, what is it? It's an integration of some quantity f on the interior of our boundary. Here's the boundary. And so we integrate f on the interior, and now the question dE by dC, what is that? Intuitively, is it tells us how does the energy change if I wiggle the boundary. This is the cost. How does that energy or cost change once I perturb the boundary? Well, there are two kinds of perturbations you can do to a boundary. You can perturb the boundary in the tangent direction. That has no effect at all. Because if you move a boundary tangentially, you don't actually see that motion. It's the same boundary. And so any motion of a point on the boundary can be decomposed in a tangential and into a normal motion. And it turns out the cost function, since we integrate over the interior, is only affected by normal motions. Tangential motions don't change the interior, and so they don't change the cost, and so not surprisingly, we only have changes in the normal direction. And what is the change? Well, if the contour evolves in the normal direction, we get another term f at that location here that is added to the energy, right? Because that comes on top of the energy. So at that pixel location x and y, what do we get? If we include that pixel into our interior, we get exactly a contribution which is f of x and y. And so this is really what it says here. Infinitesimally, the increase of the energy is by f. So it's not surprising. In fact, when I first thought what would be the right Euler-Lagrange equation, based on that intuition, I figured this must be the result, which is nice. That saves you tons of calculations if you have the right intuition. Sometimes intuitions can be misleading though, and then it's always good to do the calculations properly. So we saw that dE by dC is f times the normal. And now we said, well, what we really have, say in a two-region case, we have an interior and an exterior. And in the Mumford-Shah context, we have in the piecewise constant case, we have I minus u for the interior squared and some constant u for the exterior region squared. And now we want to know what is the functional gradient. For this part, we already saw what it is. We saw that the functional gradient is nothing but that integrand times the outer normal on the curve. Well, it turns out for the complement region, it's actually the same. Because the complement is in some sense equivalent to the interior, except that the normal is pointing the other way. Right? So we can redo the same calculations for the exterior region, and we'll find it's the same. So if NC is the outer normal, then this here is minus NC, the inner normal. And so then we get minus NC times I minus U exterior squared from the outside. And so in other words, if you perturb the boundary towards the outside, the interior region gains the point x, and so the integrand I minus U interior squared is added, and once you move it outward, what you lose in terms of cost is the exterior region gives it away, so that contributes minus I minus U exterior squared to your energy. And so this is the overall functional gradient, and at the optimum for any point along the curve, this should be 0. This should be 0, yes, so that is the result that we see here. One thing you can do to minimize this cost, once we've computed the Euler-Lagrange equation, the functional gradient, the first thing we can do for any energy, even these kinds of non-convex energies, we can do gradient descent, which means propagate the curve in direction of the negative energy. And if we plug in the functional gradient, we just saw we get this result. Due to the minus, we have the exterior term first, then the minus the interior. And interestingly, this evolution of the curve also has an extremely intuitive interpretation that makes complete sense. And that in some way is reminiscent of what region merging approaches or region growing approaches more specifically used to do. What you do at each, if you look at this gradient descent equation, what does it do? At each point of the boundary, it displaces the curve in normal direction, because we have the normal vector here. And what does the displacement depend upon? Well, it moves it outward. If this whole thing is positive, there is an outward motion. If this whole thing is negative, there is an inward motion. And what are the two cases? The outward motion emerges if that term is smaller than this term. So I minus U interior is smaller than I minus U exterior. What does that mean? It means the intensity at our boundary pixel is closer to the interior intensity than the exterior intensity. And so indeed, that's not surprising. If you ask, should I move the curve outward or inward, you check, well, I have a mean intensity U interior here, I have a mean intensity U exterior here, and so what do I want to know? Is that point closer to the inside or to the outside in terms of its brightness? And so the curve moves exactly to take that into account. It collects all the points that are more similar to one region than the competing region. And so this phenomenon, and similarly you have an inward motion in the opposite case. If the brightness is closer to the exterior, so this one is smaller than this one, then the curve should move in, basically saying the point should be attributed to the exterior region. And so you have this competition of the two adjacent regions for that boundary point. Both want the point, or don't want the point, whatever, and what affects the result is which brightness constant is closer to the current intensity. So I is always the intensity at my contour location, and U int, U x are these model intensities for the two regions. And so not surprisingly, this dynamical process that we have here was coined region competition. And I find this term is actually quite appropriate because you have two regions, I call them Ri, Rj here, the interior, the exterior. They compete for the boundary in terms of these integrands. And the region wins that has the smaller cost. So taking the point into the region, if that generates a smaller cost for inside than for outside, then the curve will move outwards to take the point to the inside region, and vice versa. So this is this region competition, and what we'll see in the following is ways and algorithms how to actually implement this kind of process. Thank you very much. That's it for today.